When we talk about data structure, we usually focus on shape, tables, trees, graphs, nested objects. But beneath the visible structure lies something far more powerful and far more important: structural invariants. These are the rules that must always remain true. Not sometimes, not usually, always. And without them, your data structure doesn't just weaken, it collapses. Today, we're exploring structural invariants, the hidden stability guarantees behind every reliable data system. So what is a structural invariant? A structural invariant is a condition that must always hold true for a data structure to remain valid. It's not about how data looks, it's about what must never break. If a structural invariant is violated, the structure is no longer trustworthy. For example, in a binary search tree, every left child must be smaller than its parent, every right child must be larger. That rule is not optional, it is invariant. Break it, and it stops being a binary search tree. In a relational database, a primary key must be unique. Break that rule, and identity collapses. An invariant defines the integrity of structure. Let's clarify something important. Structure defines shape. Constraints restrict allowed values. Invariants preserve structural truth. A constraint might say, a value must be positive, but an invariant says, the tree must remain ordered. Constraints validate data. Invariants validate structure itself. This distinction is critical, because invariants are deeper. They protect the logic of the system. Let's look at how structural invariants appear in different systems. In arrays, an array invariant might be, all elements are stored in contiguous memory. If that breaks, it's no longer an array. In linked lists, a singly linked list invariant, each node points to exactly one next node. If a node points to two or none incorrectly, the structure breaks. In graphs, a directed acyclic graph has a strict invariant, no cycles. Introduce a cycle, and it's no longer a DAG. In databases, foreign key integrity is a structural invariant. Every reference must point to an existing record. Without that invariant, relationships lose meaning. Invariants are what keep structures logically consistent. Why structural invariants matter? Structural invariants guarantee predictability, and predictability enables performance. Think about search algorithms. Binary search works only because the ordering invariant holds. Index lookups are fast only because uniqueness invariants exist. Without invariants, algorithms fail, queries slow down, systems behave unpredictably. Invariants are the reason structure is powerful. They make optimization possible. In data modeling, invariants are often implicit. For example, an order must belong to exactly one customer. A user email must uniquely identify an account. A parent entity must exist before a child entity is created. These are structural invariants. They define the semantic integrity of the model. Good data models make invariants explicit. Weak data models leave them assumed. And assumed invariants are the most dangerous, because they eventually break. When systems scale, invariants become more important, not less. Concurrency, distributed systems, microservices. The more complex the architecture, the more fragile invariants become. A distributed database must maintain consistency invariants across nodes. A cache must preserve synchronization invariants with the source of truth. Even eventual consistency models define what invariants can temporarily relax and which must never break. At scale, invariants are engineering discipline. Structural invariants don't protect themselves. We enforce them through validation logic, schema definitions, database constraints, type systems, unit tests, formal verification. Good systems check invariants constantly. Great systems design so violations are impossible. That is the difference between defensive programming and structural design. Here's the deeper idea. Structure defines possibility. Invariants define identity. Two systems may look similar on the surface, but if their invariants differ, their behavior will differ dramatically. Structural invariants are what turn shape into meaning. They are the invisible contracts that make data trustworthy. Every stable data system rests on invariants. They are silent, invisible, often unappreciated, but they are the reason your systems don't fall apart. So next time you design a data structure or a data model, ask yourself, what must always be true, because that answer defines your structure more than anything else. And that is the power of structural invariance.